look through them through the telescope?
No.
We have to see. You ever get to look through the telescope? Before you look through.
Yeah, maybe at the end of school.
Yes.
Alright, so this is the sun. The sun is not on fire. Don't believe what they tell you. The sun is a swirling ball of luminous gas. What would luminous mean?
Bright.
Bright? Luminous basically means that light comes out of it. Okay? And when we talk about gases in the sun, we're talking about two main gases. What would they be?
Helium and hydrogen.
Jump.
Roark tell me that.
That's true. Okay? So, even though, yes, it gives off light like a match or a flame or a campfire does, it is not the same thing. Campfire, you have wood that is reacting with oxygen in the air, producing a chemical reaction that gives off light. Things like that. Yes, the wood is the fuel. Here, no oxygen, so it can't be the same process. But today we need to figure out how that actually gives off light. Just the fact that you have these two elements that are there, and it's actually only one of them that is interacting to give you the light.
It's hydrogen.
Right.
Roark tell me that too.
Alright, this is what the sun looks like, or how we divide the sun up, I should say, into
How?
different
So we know. What it is.
Because we crawl right inside.
Okay? The outer portion of the sun is called the corona. You only see the corona during an eclipse. When you look at the sun, the photosphere is too bright to see the outer layers, the corona and the chromosphere. So the corona you only see during an eclipse. The photosphere is kind of the bright part. The thing we're going to talk about today is the core. The core of the sun is where all the action happens. Okay? Now, what holds things together as far as planets and suns and stuff like that? Gravity. The sun has a lot of mass. And since it has a lot of mass, it has very strong gravity. And it's that gravity that drives the internal processes that make the sun light up.
And then there's the flares. It's where the hydrogen, and since it's strong, they make a bounce off each other, and it makes then, yeah, go off.
Okay,
You also tell me that too.
you're in the right ballpark there. Okay, now we talked about the periodic table just a little, didn't we? Just a little bit.
Not really, but
We
You know what you do?
Yeah.
like how like if you add one hydrogen plus one hydrogen, and it goes like helium, and then what's that?
Yeah, that's not a lot.
So I guess we talked about this a little bit before, but in the sun you got hydrogen atoms, right?
Yep.
And those hydrogen atoms have one proton. If you remember, protons are what give an element its identity. Okay? All gold atoms have 79 protons, no more, no less. All carbon atoms have 6 protons, exactly. So the numbers up here tell you the number of protons. Hydrogen, all hydrogen atoms have 1 proton. So those hydrogen atoms are bouncing around in the sun, and because the hydrogen atoms in the middle of the atom are positive charges, they bounce off of each other. They actually don't even touch each other. They get really close, and just like magnets, they fling apart. So you take strong magnets and try to push their positive ends towards each other, they repel. And the same is true of the hydrogen atoms. So hydrogen atoms repel each other. They don't want to stick together. But because the sun is so big and there's so much gravity, it can actually squeeze them and make them come together so that they will stick. If we take two protons and we put them together, now we don't have hydrogen anymore, we have helium. So in the sun, we have this process called nuclear fusion.
Fusion.
And in nuclear fusion, two hydrogen atoms come together to make one helium.
What happens if we, okay, so if we wanted to go there, why can't we just send up like a really cold water and like kind of spread in one part, so then when we scoop it up, we can, it won't move.
Well, here's the thing. When you add water to the sun, you're adding mass. And if you add mass to the sun, what's going to happen to the gravity? More. You're going to increase. And if the gravity increases, that's actually going to make more of these molecules come together and form helium. You're actually going to make the sun burn brighter by adding water
That'd
to
be
it.
good or bad.
Because again, it's not fire, right? Yes, we're going to put fire out with water, but nuclear fusion you don't put out with water. You don't put it out. You can't. It's an internal atomic process.
So would that be bad if it got really bright?
Yeah. Well, I mean, you wouldn't have to add a lot of water to notice any kind of a difference. It would definitely get brighter. So,
Down.
this is the process that happens, but the big thing is that energy is produced. And that energy is going to come out in the form of light. As we talked about before, not just going to be visible light. There'll also be what?
Radio
Radio waves,
Microwave.
microwaves, infrawaves,
X-rays.
X-rays, UV, all of those things are given off by the sun. Now, some of those waves are blocked by the Earth's magnetic field, so they don't actually make it here. Well, violet, I guess, the color of light. Sure, we'll go with that. We'll say
Violet as well.
but some of those waves, like the UV that we can't see, still gets through some of the atmosphere, and that's why we get sunburned.
And I don't like that.
She loves it.
No.
She wants some more.
Okay? Now this process right here, nuclear fusion, the rate depends on the mass of the star. What is a rate? How fast it goes. So, the more mass there is, the harder the gravity is going to squeeze the stuff together, the more molecules are going to come together, and the faster that energy is going to be produced. So stars with more mass are going to be brighter, hotter, and they also are going to burn out much more quickly. Now that may sound weird. I mean, if you put a whole bunch of gasoline in your car, you could drive much further. But that's because in your car, the amount of gasoline that is used is kind of a constant rate. But if you think about piling up a huge pile of wood versus burning a few things of sticks, that huge pile of wood will actually burn up very quickly because there's so much fuel there. And
Burning each other.
what's that?
They'll start burning each other.
It'll start burning each other.
The wood.
Okay. All right. So the rate, the mass of the star means that bigger stars as we said, are brighter, and also hotter.
Shorter lives.
They have short lives, right? So we're going to look at some different sized stars here in a minute. We'll see things that are many more times the size that compared to our sun.
Yours is tiny.
But they will actually last less time. Our sun has an average lifespan of about 8 to 10 billion years. some of the biggest stars will actually burn out in a few thousand years. Won't last that long compared to other suns in the universe.
There was like a sun this big,
Huh?
and then our sun is like this big. It would burn for 20 billion.
It would burn much longer, yes. Some of the smallest stars, and we'll get to that are called red dwarfs, will actually burn for a few trillion years.
We read it.
Okay? So, for size comparison, each one of these pictures up here is going to kind of zoom out and show bigger things. So here's the inner planets. Which one would this be? Oh, it says up there. Mercury, Mars, Venus, and Earth. These are all arranged not in order from the sun, but in size order. Okay? Then we're going to blow up. Here would be the Earth. So we're going to shrink that down. And we have Neptune and Uranus, Saturn, and Jupiter. If we shrink Jupiter down, we see kind of the smallest star that can exist called a red dwarf. Okay, in fact, if Jupiter was about 10 times bigger, it would actually be a star. Sometimes we call it a failed star because it failed. Didn't get enough mass to actually become a star and start burning. But if it would have got enough mass, then our solar system would be a binary system with two different stars in it. It could be, yes. Okay, so then we blow up to some smaller stars here. Okay, this would be Sirius. If we take Sirius and shrink it down, then we get to Pollux, Arcturus, and Aldebaran. Oh, this is our sun here. Sorry. So our sun would be small compared to Sirius. Sirius is tiny compared to these. If we take Aldebaran and shrink it down, then some of these, Betelgeuse is a huge star. Our sun would be almost just a little dot right there compared to it. You wouldn't even you'd be able to see the Earth on that picture. Okay, and then we can shrink Betelgeuse down, and some of the biggest stars. Canis Majoris is the biggest star that we know of. And it's kind of in the end of its lifetime, which is why it has the color that it does. We're going to talk about colors here.
Wait, so what?
Go on, ladies first.
Thank you. You said red dwarf. Is it a dwarf planet?
No, it's a dwarf star. So it's a really small star. But on this, I mean, obviously the planets are not going to burn, but as far as lifetimes go, how long can they actually do nuclear fusion? The time goes down as you go up in size. So these would be very short-lived stars. They're very young. They haven't been along a very long time. These stars down here are going to be around much longer. So our star is kind of average, so it's going to last a pretty decent time. Not as long as the longest stars, but definitely not as short as the shortest lived stars. Right? Okay, so this kind of gives the same idea. This would be a yellow dwarf star, which would be like our sun. Our sun is technically a dwarf star, but it's not as far. It's like a red dwarf. Even though there's things called brown dwarfs out there. But we tend to see that the biggest stars are kind of bluish in color. Smaller stars are red. Now, there are some differences there. You will find some big red stars, and we'll talk about that in a minute. But for the most part, when you look at stars and you look at their sizes, blue ones are really big and short-lived. Red ones tend to be fairly small. Our sun is yellow, kind of. It's sort of in the middle. Okay, this shows kind of the same thing. So when we look at stars and we see colors, what we're basically seeing is how hot that star is. Kind of. But the problem there with equating it to thermal images is that you have a computer that is just making colors for you to see. This would be more like if you have ever taken a piece of steel and heated it under a torch and gotten it really hot, and it starts to glow. It'll glow red to begin with, and then it'll get more towards kind of the white if you get it really, really hot. So that's what happens with stars. Okay? Red stars, which are cooler, okay? When we look at the light that's given off, it does give off all different forms of light, but the peak, the light that it gives the most off of, is going to be kind of in the red. Okay? Yellow stars, like our sun, give off a bunch of wavelengths, and as far as the visible light that we see, it kind of peaks in the middle. So the peak wavelength is going to be around the green, but our sun doesn't look green because it's also giving off all of these other colors kind of equal. Really hot stars are going to peak actually in the ultraviolet, and so most of the light that we see given off is going to be blue. And so the temperature of the star kind of corresponds to its color. Hot stars, see, we can see this star is only about 2,500 Kelvin, are going to look red. Kind of in the middle, those stars are going to be look whitish or yellowish, around 6,000 Kelvin for that one. And then the really hot stars are going to look bluish. Okay? So, as far as stars go, we can classify them based on color. We can classify them based on size. And then we're looking at the mass of the star. And we can also classify them based on what we call luminosity. What would luminosity mean?
Illuminate. How bright it is.
How bright it is. Brightness. And for the most part, hotter stars are also brighter stars. They have more energy. Okay, now the problem is that this all makes sense as long as we're looking at stars that are kind of in the middle of their life. But when stars die, they change.
Dude, I want to say this.
Okay, Alyssa, say what you would like to say.
They can create black holes, supernovas.
That's after death.
I know how they die.
Okay?
Once they create just one atom of iron, or some, what was it? I think it was iron. Whatever,
It wouldn't be one atom.
some of it. And then it can't push out anymore, so it all collapses in because of all the gravity.
Okay. We're going to talk about that. You're mostly on the right page there. But eventually, our star, which is kind of a normal size reddish star, or yellowish star, is actually going to expand many times its size for some reasons that we will talk about next week. And eventually, it's going to get so far out, I think we've talked about this before, it will eat up Mercury and Venus. It might get out as far as Earth and Mars. It kind of depends on how things happen. We're not sure as far as that goes. But it's also going to cool down and change color to red. And so eventually our sun will become what's called a red giant.
You think those have a blue?
No, our star doesn't have enough mass to ever burn bright enough to be blue. So, we won't ever see a blue star, but it will eventually become a red giant. And that's going to happen during its death. So stars will change as they die. Okay, and here's where the Hertzsprung-Russell diagram that you guys drew comes in, because it's a way of kind of looking at the different stars based on a couple of things and how they fit along with each other. Okay, this is just a good a kind of a comparison of different colors based on the temperatures, and as we said before, blue ones are really hot, red ones fairly cool. Now, 2,000 to 3,000 degrees Celsius is still pretty hot for us, but for a star, that's pretty cold. That's ice cold. So here's the Hertzsprung-Russell diagram. And it's named that because you guys developed it, and their last names were Hertzsprung and Russell. But we tend to just call this the HR diagram. Okay? The point of the HR diagram is to kind of graph out the different stars based on a couple of characteristics. So here, they're graphing out based on brightness on one axis, and on the other axis, temperature. Okay? As we can see, most of the stars fall into this kind of swath that goes from here up to here, and we call that the main sequence. The main sequence basically shows stars where they're graphed during the majority of their lifetime. So normal life, a star is going to fall somewhere on the main sequence. Really big stars during their normal life would be up here. They're really bright and really hot. Really small stars during the normal life are going to be down here. They're really cool and not very bright at all, dim. Our sun is right in here, kind of in the middle. What's that?
You said it's a sexy beast.
Okay. That's not weird at all. Now, what happens though, as stars lose their fuel and they grow and they dim, they go into this part right up here. This is where we see Betelgeuse, which is a red giant. And this is basically where stars get graphed when they are dying. So, eventually our sun will run out of its fuel, it will expand, it will dim, it will actually cool down, even though it's going to destroy the Earth. That's just because it's going to come so close to us. It will actually cool down and dim, and it will be up here in this portion. And then eventually, as those stars completely lose their fuel, they will become very dim and hot stars called white dwarfs. So down here is the section of white dwarfs. And that's one thing that can happen to a star when it dies. So next week we'll be talking about white dwarfs, neutron stars, black holes, all those sorts of things.
What are the ones called where they turn into diamonds? It's just a big chunk of diamond.
Coal. That's white dwarf.
Oh.
I hope one of them lands Wait, near Earth. Well, do you think?
I mean, it goes beyond the whole diamond thing because of what happens to the atoms, but ostensibly it's just a big chunk of carbon. Yes?
Do you think in the future, anytime that we're going to find a blue sun that's so hot it spews out blue fire?
No fire. Remember, there's no fire. It's fusion.
It can be fire.
It's
No, it's
liquid.
impossible for
Liquid
fire
gas.
to burn in space.
Now we put gasoline in the case.
There's no oxygen. Therefore, it cannot burn.
Okay, now here's a question. Let's say we followed a group of stars and we graphed them on the main sequence from the first that they were born. Which of those stars would start to disappear and go into the dying stars first?
The blue.
Blue giant.
Right, the big blue ones up here, right? They're going to burn out of their fuel very quickly. And so what we will see is that over time, these stars will disappear. They'll get graphed over here. We won't see any of these stars, and they'll eventually move down here. And so over time, these stars will disappear down the main sequence. And so what this helps us do is we can look at galaxies, and we can look at star clusters, and by graphing out their main sequence, we can actually kind of figure out how old those galaxies and star clusters are. Because if there's a whole bunch of blue stars up in here, we know that that galaxy or star cluster is pretty young, because those haven't had time to burn out yet. If we look and there's no blue stars and they're all down here, that cluster of stars must be pretty old, because all of these have gone already. Yeah?
Okay, so one day there won't be like any stars.
Right. Now that will take trillions of years. You don't need to
I'm
worry
gonna
about
live
that.
that long, guys.
But yes, you are right. Eventually, all the stars will burn out, and there will be no stars left in the universe.
That would be weird.
That would be weird. It's called the heat death of the universe.
No hydrogen left.
There'll be hydrogen left. There just won't be enough to stoke the future.
So space is just gonna be nothing but a big black hole.
Yes.
It's up to just, well,
So here's an example of a star cluster. And as we said, we can age the star cluster based on the types of stars. Okay, and we're going to watch a video here that's going to show you an animation of how they kind of do that. And this star cluster is going to have thousands of stars in it. Pause this for a minute.
Hello, YouTube.
Do you have a question, Justin?
So when I get my big diamond, how big is it gonna be?
You're talking about trying to get a white dwarf?
Yep.
It would be about the size of New York, but it would weigh as much as, almost as much as the sun. So.
I'll probably just have my wife just put it
All right.
Today on page 4, we'll be talking about clusters. Like, comment, and subscribe for more.
Thank you, Trace. That's
You're
very
welcome.
helpful.
You got my subscription trace.
If you look at this picture of a star cluster, based on the stars that are there, just as kind of a rough estimate, what do you think? Is this old or young?
Old. I think both of them are
young,
young.
middle, or middle age.
They're old because they're all white.
Is that racist?
Yeah, if you want it to be.
Those look all white to you?
There's a lot of old. Yeah.
There's quite a few
I don't know. I see a whole bunch of blue on there.
I don't see.
I see
any. I see a lot of white. I see a lot of white.
Maybe I'm just used to looking at it on the computer where you can see the colors a little bit better. All right, I'm going to tell you, there's a bunch of blue stars on here. So would you say that that's young or old?
Young.
They are young.
Young.
The blue ones are young.
Because remember, if there's blue stars on this star cluster should be fairly young as far as these things go. Yes.
Couldn't all the blue ones be at the very end of their life?
Yeah, and that makes it a little bit hard but they last so long. They last so few years, or thousands of years in that area. We tend to see very few stars that are actually there. So if there's a lot of blue stars, that means it's. So that's a good point. But just because there's so few of them that we're gonna catch in that state of the final acts of dying, those are fairly rare. So we don't see too many.
I think that's pretty much all I have for today.
I really like this one.
Goodbye, YouTube. Goodbye.